All right. Good afternoon, everyone, and welcome to the third and last of this year's Data Science for Social Impact postdoctoral webinars. Thanks for people who've come in for all of them. It's been a great response from the community. And today we're going to have the third and final one. Today we're going to have Dr. Hope Mogale on the topic
There's
of...
only me here.
Oh, sorry.
Okay, there's other people.
Oh, sorry. Let me just check there.
Yeah. Oh, there.
Okay. As always, these things, that is very odd. I thought it was not supposed to happen. Okay. Thanks for joining for this one. We will have Dr. Hope Mogale today. We're on designing automatic speech recognition systems to perform well and scale to South African low resource languages. Dr. Mogale is a South African-born computer scientist with a PhD in computer science from Northwest University. His research spans across machine learning, AI, and natural language processing, with a particular focus on developing technologies for low-resource African languages. He specializes in LLMs, generative AI, and high-performance computing, and has also worked in advanced computing architectures like ASICs and FPGAs and parallel deep neural networks. He's currently a senior member of the DSFSI lab at the University of Pretoria and a postdoctoral fellow who is funded by Microsoft Research Africa. And we really want to say thanks to Microsoft Research Africa for this opportunity, as well as our Department of Research and Innovation here at the University of Pretoria. His work addresses challenges in ASR, and he focuses on looking at robust ASR systems in that perform well on low resource datasets. Right. Through his work on NLP and self-supervised learning, he's exploring innovative ways to bridge the language divide and improve access to AI-driven speech technologies on the continent. We're also very thankful for some of our collaborators who come in from Stellenbosch University and other universities, as well as MSR Africa, who might be on this call. And with that, I will hand over to Hope. Just as normal, we would have about 40 minutes of him presenting. I will give him a 5-minute warning, and then after that, we will do Q&A. All right, Hope, over to you.
Thank you, Prof. Good afternoon, everyone. My name is Hope Mogale. You guys can just call me Hope. I would like to welcome you into this seminar, and I will begin shortly with my talk. And just before we start, I would just like to thank DFSI for the opportunity, the guys at Microsoft for the opportunity, and the whole research community, specifically African researchers that are pushing the envelope of AI. It's been amazing to learn from them, from the Deep Learning Indaba crew, to all the other guys that are involved in NLP, linguistics, Hunzula, and all the other teams. It is inspiring to see Africa standing up and not letting other countries build for us. And I got to learn a lot because of that. And back then, we used to really not have a community like that. So I'd like to say, let's keep growing and let's keep going forward. Okay, thank you. I will now start to share my my talk. Okay. Can you guys see my screen?
Yes, you can go ahead.
Okay, thank you, Prof. So as I've introduced myself, my name is Hope Mogale, and I will be presenting on designing automatic speech recognition systems that perform well and scale on African low resource language. As the title of the talk, it's to teach people how to design these systems from end to end, especially for African low resource languages. And I believe that this is a very critical skill, because Africa, it's the one with more languages, and it's the one that is really diverse, and culturally diverse, and has so many regions, and almost in Africa, like a new language gets born before another one dies, and African languages live very, very long, and therefore we cannot let other people from other countries to try to build from us. If there are intelligence systems that will be multilingual, they must come from Africa. And learning how to build systems that can handle these languages well is very crucial and critical. So my research work is not necessarily going to be intensely on um, you know, showing you a couple of experiments that I did and then showing you guys results, because we all know that, like, that is just the usual. What it'll be, though, it'll be made up of different sections whereby I talk about system design, and I talk about demos, and then I show the results of that, and how that performs, and how that scales well on African low resource languages. And we shall learn a lot by also understanding the theoretical background, and also doing and implementing and seeing that work in action. Okay, so I'll proceed. So this is a very important graph that really shaped my perspective about speech, because speech is hard. Teaching computers to learn how to interpret speech, it's not an easy job. Just like even a human, when it's still at a baby form, takes a while before they learn speech. They might learn how to even walk before they learn how to process speech, and use it and interpret it. And even when you still grow up, you're still learning words like schizophrenia. What are those words meaning and all that? So speech is sort of like endless. But basically, God put us on this earth, and on this earth we have what we call a dynamic range, meaning the earth itself, it's a room that we all live inside of, and it has its own dynamic range that allows us to mimic sounds. Like birds make their sounds, humans make their sounds, and all of that. And as we have instruments on the sides of our heads, and these instruments are called ears, and these ears basically pick up frequencies. That is, they pick up vibrations, um, 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 and interpret them in different frequency levels. And this is all summarized as the Fletcher-Munson curves. So sound, basically, we simply say that sound is nothing but Fletcher-Munson curves. And these are very important curves, because they reflect just how the human ear is able to interpret the different frequencies of sound, from low end frequencies to high end frequencies, and how we can classify those. And later on the talk, we will see how we will be able to also still use this curve, and make informed decisions that will help the systems that we're going to design to sort of like take intelligent decisions about sound. But uh, uh, if we were in a different planet, then this might not have been the case. Our atmosphere is quite silent, and it is giving us a room whereby we can be able to play around with different sounds, and we can become audible. All right. So how do humans do it? As I said, we have instruments called ears, and our ears, they are hardwired naturally to interpret the different vibrations of sound, and we can basically articulate. When we hear a bass frequency, we can articulate that as a bass frequency. When we hear some sort of like a bit of a rumbling out of the blue, we tend to like get scared, because we have already like sort of like put in our database what all different sounds mean and so forth. When we hear a sounding alarm, we expect the cops and all of that. All of that is baked into a human, and a human can be able to understand all of these phenomenons easily. But for a computer system, that is a totally different thing. And humans learn faster because they are sort of like multimodal by nature, and they observe a lot of things using their eyes and interpreting the environment around them. And obviously AI, we're trying to model it after humans. We're trying to create something that is more intelligent than us. But first we have to surpass the human intelligence and so forth. And that's what these ASR systems are going to be like. They're going to first get to the human level of understanding sounds, and then now use advanced techniques such as natural language processing to be able to understand and articulate sound and convey meaning and so forth. Right. So how might computers do this? Well, first of all, obviously, will be through digitization, because computers work with zeros and ones. And from there, now we perform acoustic analysis of the speech signal, and linguistic interpretation, because sound tend to come as a packet, and as it comes as a packet, it may be having background noise. Maybe when that sound was recorded, somebody was using a grinder in the background, or a car was passing by and so forth. So we end up having, in the dynamic range, we end up having things like background noise that are sort of like obstructing and so forth. All of that needs to be digitized and analyzed, and different features of speech data needs to be labeled to say that, okay, this is that, that is that, that is that. But that is not our primary concern. Here we're going to be working on ASR systems, and we assume that the best case scenario that we'll be working with is that we will work with clean sound that is just speech sound, and we have eliminated all the obstructions of background noise and so forth. Obviously there will be cases whereby we do encounter background noise, but we can teach these systems to sort of like ignore that, and just focus on speeches. And applications of this is currently being in use. Like, if you use modern day wireless earbuds, you notice that they can be able to isolate background noises and just give you adaptive noise cancellation systems and so forth. So that is just all in speech processing and its applications and so forth. Right. So now we said that the way that computers might go with it about this is through digitization. But what's really hard about digitization, and this is something that a researcher needs to really understand very well in order for him to be able to excel when designing effective automatic speech recognition systems, is really knowing how to take it from um, its analog version to digitizing it effectively, and not leaving any information out of that speech data. So with digitization, we basically convert these analog signals, because sound is analog by nature, into digital representation. Digital representation, then that's when now we can play with zeros and ones, and we can start using processing units such as GPUs, CPUs, APUs, and so forth. And then now with signal processing, then we can go ahead and separate speech from background noise. So basically, we will identify different kinds of noise. There's brown noise, pink noise, white noise, and so forth. You've encountered things like white noise when you are using a radio, and you're kind of like trying to wind it to sort of like on a car, or at home, trying to wind it to reach the station that you want to reach. You might hear that shh sound as you're trying to go through the different frequencies to get to the point whereby you are reaching your station. But those used to be analog systems struggling with that. With digital systems, They come with auto search functions that have that background noise removed and so forth. So background noise is available in different formats, whether sound was recorded on a phone or whether sound was recorded, in different kinds of rooms. There will be some dynamic range that comes in a form of noise. So signal processing becomes very important. Then next is phonetics, which is variability in human speech. We will have this by nature because human beings tend to express themselves differently. It depends on what is the situation, how are they feeling. Is there an emergency? When there's an emergency, people usually shout or try to warn you or try to tell you get off the road or something like that and all that. So there will be variability in different human speech, and we have to be able to recognize that. We have to be able to recognize the different exclamations and so forth. And then there's also phonology, which is recognizing the individual sound distinctions, the similar phonemes. And then lexicology and syntax, disambiguating between hormones, features of continuous speech, and then syntax pragmatics and different pragmatics. So all of these things, sort of like when you take them all together and you put them all together, they kind of like sort of like make this not just a walk in the park kind of a job, because you have to be really, really invested in in getting all these variables right in order for you to perform effective speech recognition. So then basically what digitization involves is, taking analog signals and converting them into digital conversions. Usually this happens primarily through a device called a microphone that is able to capture these frequencies and store them into speech format type of data that is digitized and converted into different compression methods that we use to store sound data, right? Which can be either MPEG-4, or it could be wave, or it could be MP3, or and so forth. And then what follows with digitization will be sampling and quantization. And this is very, very, very important. And we will see on when I'm demoing some of the systems on the chosen sampling and quantization of speech data, why it's basically needed. It's needed because different levels of sampling allows you to sort of like create different rooms and different performance of sound. Sound needs a very good headroom, and when you are sampling it, you have to be careful about that. You have to be careful about that. For example, we primarily use 16 kilohertz because 16 kilohertz, it's a very good balance, strikes a good balance in terms of storing sound information or speech data information without compromising its content and compressing it too much. And also, because we're working with large data sets, we don't want our models to sort of like, per file be choking or like not performing well and taking longer than required. So sampling with 16 kilohertz, as we've tested all the different other formats, was that it performed way well, and it took less resources, because in data science, resources are very, very, very scarce, and you can't just play around with resources. You have to be very, very efficient with them. Besides that, really, models tend to be performing very well when you have struck a good balance in terms of sampling and quantization. Quantization basically would be, the different compression formats that you might work with and, use without also scaling down sound to a point whereby it's inaudible, or, these models, as they are training, are able to unable to work with that, or basically you know uh, uh, interpret that or recognize that. So then we use filters and all different kinds of sound processing units to measure energy levels of various points and frequency spectrum. And um, if you know the different frequencies, then this makes the job easier. And I think I'll show this in the second slide from now on, to express why this plays a good role, or why this plays an important role. Knowing which frequency is responsible for which sound makes it easier for you to sort of like debug or build these systems and so forth. So, for example, high frequency sounds are less informative, so can be sampled using broader bandwidth or just basically the log scale. And you'd find that in most cases, even the humans, in most cases, the humans are always losing low frequency. A monologue or a dialogue in a normal room, everywhere on Earth, it's usually leaning towards low frequencies, because human beings don't spend time like sitting in a room and shouting at each other. That occurs every once in a while, and the shouting may raise the frequency bars and start to hit on the mid frequencies, going all the way up into the higher frequencies. But normal audio, like normal speech, is just basically just two human beings just talking to each other on a normal lower mid frequencies going down to the low frequencies. So those tend to be the ones that are having really a lot of good information.
Yeah, Hope. Just given your, I know your presentation. You got about 20 minutes left. Yeah.
Okay. Thank you. And then as I talked about this, then we have different tools that allows us to separate speech from background noise, right? So now we come to understanding the dynamics of the two most important uh, people in society, which is a male and a female, right? So um, we see over here that we have different curves for just casual conversation, and then also just for normal conversation, and for raised, and for loud, and for shouted, right? uh, and you can basically see the different sound pressure levels on where they begin and where they end. And if you look at them from the male perspective, you will notice that they are sort of like a bit different, although similar, but they are a bit different. And you will notice that males tend to lean towards more of lower frequencies, whereas females by default, they start from mid high frequencies, moving all the way to um, to to high frequencies, and spend most of the time on the high frequencies. Even young females, when they speak, most of them are just on mid high frequencies. And we will demonstrate this briefly, just and see this in action. All right. So when working with low resource African languages, I think I'm done with the theory part now. We about to get to mostly the implementation part. I just needed to have a good background laid up on that. Is that when working with low resource African languages, we have the different types of languages. Obviously, the Niger Congo languages, and the Afro-Asiatic languages, also the Afro-Nama and the Khoi, sort of like languages and so forth. And different languages fall within different speech data sets and corpus that are sort of like available. So we have NCHLT, Lwazi, Lacunas, Afri-Speech, African Common Voice, and Niger Volta, Low Resource West African. So the main thing to study here is that these data sets, um, uh, all of them tend to come with um, different formats, right? They tend to come with different formats, and when they come with different formats, that present sort of like a challenge for our system, because our system needs to feed on a data set before we can be able to do anything. The first part is us just basically loading our data set and working with that. So in a way, you could sort of like think of it this way, because these are, like these are speech data sets that are available, and they're sort of like large, and funding had to be given away for these projects to be initiated and to be put up there. As an individual researcher, it will be sort of like hard for you to find the resources, the funding, and all of that in order for you um, um, to create your own data set, basically, that is large enough to do ASR. Because for ASR, you really need large hours and large size data set. So this is very, very key and important. If you don't understand this part, no matter how much I can explain the technical part or show you, it'll be just hard for you to design systems for low resource African languages. So the way I want you to think about this is, think of each and every single data set that is available, because what's going to happen is, as time goes on, there will be new data sets that are being introduced. And these new data sets that are being introduced, each and every one of them will still come with their own formats and so forth. So therefore, when you build a system, you need to make it to be able to adapt to this, to be able to adapt to this, to be able to understand how to load an NCHLT speech corpus, how to load a Lwazi, how to load a common voice, how to load something from Hugging Face or Kaggle or and so forth. So the way to do this is, obtain a sample of each and every one of them, study the formats, what's being used over there, the CSVs, the text formats, and all of that. And then now start to now backtrack and design to say the system must be able to recognize this, the system must be able to recognize this. Or one way is to basically create a middleware that will take, an existing NCHLT speech corpus, and then it translates all of that data set into, or pre-processes it into, what your system basically understand. I usually just opt for, because I believe if you just do it once and you've created a system that is able to just understand how to load Lwazi's speech data set, or NCHLT's speech data set, or Masakane or whatsoever, then you've done it once, and these data sets, they'll keep evolving and keep growing and keep, and your system will still be able to be used by different researchers, and it will still just work, and there will be not much of a failure. So I think if I can just make a simple demo of this. Um, okay. Okay. Okay, let me just share the screen. All right, so this is an ASR model trainer and fine tuner. So if I click on the dataset source over here, you will notice that what's launched over here is ANC, HLT, Lwazi, West African voices, and so forth. Different kinds of formats, right? So I will go ahead and just load a Setswana Lwazi dataset, right? And click on import dataset and go to ASR and go to datasets. And you will notice there will be like different kinds of datasets that are over here. I'll select Lwazi and just load the Setswana Lwazi dataset. And when I open it, it should be able to open and tell me that, There's male 96 and 96 females that are available, different age sizes and so forth, and tell me that this is Setswana with 7.9 hours and 203 speakers that have been identified. And I can go ahead and pre-process this, split the data into both test and validation and so forth. So let me go and load Common Voice. This time I might just choose Yoruba Common Voice. So let me just remove this data set and then just load a Common Voice Yoruba data set. And successfully loaded Yoruba 7.6 100 speakers of Common Voice dataset. This dataset was basically just obtained from Common Voice public um, library that allows everyone to basically just obtain that dataset and play around with. So being able to switch between the different data sets is key in designing these systems. It's sort of like key in designing these systems. Okay, just present this. Right. Then, I present the first ASR system and how it was basically designed, which is basically we have the front end layer, which has the UI layer that allows the user to go ahead and make informed decisions. And then now there'll be view panels and control panels over there. And then now the core engine, which will have the audio manager and the model manager. And then we will utilize the Whisper model to perform things like language detection, and translation manager is assisted by things like TTS model and the likes of the M2M100 or NLB or XLM Roberta, and also speech brain and also PyAnnotate to be able to allow us to basically perform things, advanced features such as speech diarization that are also potential threat into designing systems that are like this. Okay, so let me just demo this very quick. Let me just share the screen. Okay, so this is the ASR Research Suite. It has a bunch of models that are there and allows you to load your speech data. And the chosen format, as I've been explaining in the previous slide, is basically 16 kilohertz of wave audio that is allowed in and that works well with most data sets, also with most systems. By the way, you will find a lot of data sets in different formats. Try to pre-process them and sort of also try to work with 16 kilohertz. So I'll go ahead and just load audio and choose one of the things. So I'll go ahead and just choose a simple, just Xhosa speech data, just the short speech data. And I'll go ahead and just choose Whisper Small. This is a Whisper fine-tuned model on Xhosa. And, we will see how this model was basically created and for it to be able to perform the way it performs. Now, if I play the this speech file over here, we could hear it speaking in Xhosa.
Abantu abafuni ukumamela mama.
And then I'll go ahead and transcribe that using that. and we see that it has transcribed and said abantu abafuna ukumamela mama, as it is saying over there. If I just clear this out and try to use Whisper Small, the normal out of the base Whisper Small, it won't be able to transcribe this. It will just try to give out some stuff, but it won't be able to do that because it isn't trained on doing that. But if I am to just choose it and I just go ahead and just load test speech that is in English, like this one over here, I'll clear the text over here and transcribe it. We see that it successfully transcribed this, which simply, if I play it, it will say,
dancing in the masquerade, idle truth in plain sight jaded, pop, roll, click, shot, who will I be today or not?
But such a tide as moving seems asleep, too full for sound and foam, when that which drew from out the boundless deep turns again home, twilight and evening bell, and after that.
Yeah, we see that it's able to transcribe that, but it's not specialized on low resource language. And basically, we also can do NLP translation and translate this into Afrikaans or different language that we may want to. I'll just get back to the presentation quickly. We'll get back to this. Right. So basically, the training architecture of the fine-tuning suite, which I will go ahead and demo next. Basically, what it does is it takes sound and speech data, turns it into text labels, which will go ahead and hold the transcriptions. And then the other label that it does is basically to hold all the different audio features that I talked about, from phonemes to frequency ranges and different kinds of audio um, speech information. And we use a numpy array, and it's able to basically just hold this and put it in different dictionaries, and now tokenize this, and be able to prepare it for PyTorch. And then now what's basically outputted will be then the base model and the PEFT adapter, and these both from both labels, they end up connecting to the training loop. And then now we can just keep going back to the checkpoints, and if we see from the checkpoints that we are still allowed to train, then the cycle continues over and over again. So you have your input layer and the output layer and the model components. At the heart of this, obviously, is the Whisper architecture by OpenAI. I'm not going to get into too much details about this, because if you work with, if you work with ASR, then you are likely to mostly encounter this. But basically, this just have both encoder and decoder blocks that just basically use transformers to be able to do this. Okay, so one of the problems that you will encounter with speech data is
Hope just 5 minutes. Yeah.
Yeah. I'm almost done, bro. Is that you will find that most of this speech tend to come also in dialogue data, whereby you have two speakers that are speaking over there. And also, if you listen to TV or radio, that is the case. So remember, we are designing these systems for machines. So they are going to also interpret environments whereby there are more than just one human speaking. And therefore, this is when diarization basically just comes in. So if I can just go and also illustrate this, I will go to the window over here. Right. So then from this speech that we heard that we had two people over here, which is a male and a female. And we can go ahead and just basically uh, diarize that, and then it will now basically just separate both the speakers, both male and female speakers, and then identify their speech to say that, okay, the female said this part, and then the male said that part. And the way it's able to basically just do that is that it it used the different frequency ranges that I was talking about. And basically what it does is it goes through the whole speech file that we see over here, and it now scans which frequencies are mostly on the mid high frequencies going into the high frequencies. And when it discovers that, it then identifies those as female, and then those that are mostly low frequencies, it goes ahead and identify those as low, as male. But usually what it does is it can tell the different variability in articulation, because everybody has their own accent in a way. And with that articulation, then you can start to see that, okay, for speech one, what we simply had was the first person, when they were articulating, they are constant lied at this particular range of frequencies, and the other one lied over here. So on this speech, we heard the female saying, dancing in the masquerade, adult truth, plain side, jaded, pop, roll, click short, who will I be today, or, and then not. This not is supposed to be on the female side, but because the female said the not in a lower tone, the system was able to basically classify it as also as part of the male speech, and hence why you still find it on the male box speech over here. And that's what basically happened. I also have another speech over here of a mother and daughter. So I will just clear this up and then play it. You will notice that this is basically also again. It'll
Mama, oko kufike usana olutsha. Awunaxesha lam.
Yiza apha sithandwa sam. Wena nodade wakho ningabona bantu babalulekileyo ebomini bam.
So I'll go ahead and use the cursor model and just transcribe this. You should be able to transcribe it. And then basically it has done so. And if I diarize this, you'll see a totally different output. What the system will think will be that because the child's voice is so much of sort of like in a higher pitch, it turned to have identified the child as the female, and it has put the child in the female box part, and then it has taken the mother and put the mother in the male box part, because the mother's sounded more of thick and was sort of like showing a lot of um, uh, uh, response in the lower mid frequencies going over here, as you can see, as it is diarized, and it's able to basically do that. So basically, when we have our system being able to perform like that and just basically identify um, identify the different speakers that are like for different species, then we are able to perform design systems that are able to scale and are not going to be abstracted whenever we hear one or two speakers, right? And basically this was like the training flow. I would have loved to demonstrate this on how such models are created, how they are how we use the fine-tuning system to basically create those models and how they are performing. But I think because of time, we will be limited by that. And then these were some of the initial results that we're encountering earlier on, and these were not really good results. That there was a lot of improvement, room of improvement that we needed to do on the system. I couldn't even perform diarization, but given enough time and enough training, we were able to basically now do that. Some of the stuff that was prescribed, you know, was sort of like even unreadable. But if you just, you know, as you can see, this was just 2.5 hours speech data. This, you can go far with that. You need at least about, you know, about 50 hours of speech data to about 100 hours of speech data for you to be able to perform effective um, uh, automatic speech recognition. And with that, I would like to just say thank you.
Okay. Yeah. Thanks. Thanks a lot. Hope for that presentation. I think it's a a different type of presentation given the other typical ones inside this I mean these seminars, so being able to go through and up, like, you know, building up a interface to assist also in this space to people to explore their data and then move towards training. Maybe I thought as a question is that can you talk a bit maybe on some of the full features of your tool? And then do you also expect that the tool is going to be available for people as well?
Um, yes, Prof. Obviously, we honestly, you know, for this whole talk, I would like to thank Dr. Kayode Olale. He was the first one that when I got to the lab, who put me up to full speed with you know, designing these tools and ASR in general. Like, he took me from A to Z in terms of that, and he's you know, very talented and well seasoned, and I work with him, you know, hand to hand and all of that. The end goal is to have this available for people to be able to work with. So obviously through the lab, through data sharing, and through you know, clearing of what needs to be cleared, and also still fine tuning it, because it may look like it is good. There are still some features that need to go through, that need to be implemented, and that need to be polished. But the end goal is to have it out there for people to be using it, and for people to be working on, and, you know, us seeing the different results that they've achieved, and also them making recommendations to say, hey, can you improve on this, and can we have this, and as we introduce the different features. Yeah. So the end goal is to basically have it out there and put it on different researchers' hands, because then, you know, I believe that African researchers are way more creative, and they will also take it to another level. Yeah.
Oh, okay. Thanks. Maybe you can stop sharing your screen.
Okay.
A question. Yeah. Also, for everybody on the call, if you want to ask your question, we will. You can just raise your hand, and you can ask. But then for now, I'll just read some questions for you. Hope. Okay. Clinton, maybe you might want to unmute and ask your question. I think maybe it might not be full context there.
Good afternoon. Am I audible inside?
Yes.
Yeah,
Okay.
you are.
Okay. I'm currently doing a research on what you are researching, but mine it's a little bit different, because it's more like it's end-to-end speech recognition for low resource Tsonga in mental health support. So my question, it goes to all the tools. What kind of tools were you using from collecting data to training? Which tools were you relying on the most? Which they were very helpful. Thank you.
Okay. Thank you. The main tool is Python. It's the tool that is able to build other tools. You know, what I found out earlier on was that there aren't as many tools out there that have been built and that have been made available. And so, you know, like that led to me being innovative and being like, well, how can I sort of like automate this process of data collection, of pre-processing audio data and audio speech data. And at first it was a struggle. I needed to give it a lot of time and a lot of thought and a lot of going back into the drawing board and iterating. I think we started working on this since last year, July. Yeah. And went through so many iterations and iterations and iterations. But I think as time goes on, tools like this will become available. And for people like you and for researchers like you, then it wouldn't be that hard to be able to perform your work and be able to get your end goal and reach the end goal of your research and the outcomes that you want to reach and so forth. So which is something that I recommend forward for us Africans, is that we are limited in so many things, tools, computers, and all of that. So we really have to find innovative ways and work together and see where we can assist each other and so forth. So you know, uh, coding skills helped a lot, and a lot of Python, a lot of researching, a lot of there is a lot of YouTubers as well who were helping here and there and all that. But most of the work was just me figuring it out where I failed and coming back to that era and iterating and looping forward until I got to the end goal.
Okay, cool. And then I think a few other things that London is that yes, I think in terms of training, it was training Whisper. There's Web2Vec, the data. Some of it is as Hope has said is available, but then it's just that you have to standardize it into a format that you are comfortable with. So I think some of that he's provided some ways that you can then deal with that. At the moment, okay, we'll go to Tapelo before I read some more questions.
Am I audible, Prof?
Yes.
All right. Thank you so much, Prof. Vukosi, for organizing this seminar, and thank you so much, Dr. Hope, for this insightful talk. I just have a few questions. The first one is, have you, in terms of reporting, have you gave like a clear overview of what amount of resources do you need to get started with implementing the solution that you have implemented in terms of GPUs, what computing power do you need, and all that. The second one is in terms of coverage, how many languages, low resource languages, does your ASR system cover, like the South African languages? And then the last one is in terms of this. Just please answer those two until I forget. I remember the next one.
Okay. So in terms of an overview of the resources that you can basically start with, I'd say that if you just have access to a laptop, that is your starting point. Just like a lot of people often say that if you want to get into YouTubing, the first camera, whether it's your phone, it's what you start with, and your needs will start to grow over there over time, and sort of like start to incrementally become that. So when I started, I realized that looking at all these requirements and looking at all, they sort of like gave me anxiety, and the anxiety really sort of like crippled me, and I didn't want to like get started because I felt like I didn't have access to a whole lot of resources, and I couldn't do much and all of that. But then as as time went by, and I just started to realize that okay, actually really what's not needed, it's really not much. It's just me just sitting down and defining and sort of like abstracting all this problem that I'm trying to solve into smaller parts there and smaller steps that I'm able to basically tackle those at a time. So you're looking at this as a final end goal. It's looking amazing and all that. But if you look at this, if you break it down, it's actually just 1,000 Python notebooks, basically. And these 1,000 Python notebooks, I used to show Prof the notebooks, like, it was just a whole lot of fragmented notebooks and all of that. And then they all sort of like now started to come together. Each notebook was addressing a certain part. And then I put everything else all together. And then now the elephant in the room was the training part. And how do I overcome this? And when you have covered so much ground, you wouldn't let something like training get in the way. Obviously, you will find a way to get access to, a GPU. And yeah, I'm saying this for the general people out there so that they can know that, just because you don't have access to powerful computing resources doesn't mean that you shouldn't get started with this. Start with the smaller things, abstract to the smaller things and start to learn the fundamentals and learn all of that. And then when it comes to your second question, that this can address any language, as I said, that what we basically do is, the most important part is, even though the data sets and even though languages come in different, formats, we have agglutinative languages, you have different kinds of languages, like Afrikaans is like sort of like a bit congested and it has a lot of technical terms on it and it gets complex very quickly. So, I had to find a way in that, okay, one thing stays consistent. And that thing that stays consistent is basically I leveraged NLP, and that NLP is already developed because it didn't have much of a larger development curve because we're just working with text. And NLP was bound to basically develop. If you got linguists and access to just data, then NLP will develop, of which that is available through the internet. And it has developed and gotten so good over the years. And then now the second part was, then okay, then how do we become innovative with the speech part, and then now turn these into also like bits and pieces that can become vectors and work with that, so that each and every language can become covered. And as long as you fine tune using these systems, you should be able to, if you have just high quality data set, you should be able to do that. So then a lot of standardization had to go in place. And with so much that I have tested through, I was able to basically just achieve good results on most of the low resource languages. Obviously, a lot of testing is still going on, and a lot of improvements are still going through. Yes.
Okay.
Thanks,
Just
Dr.
a quick one with a couple of questions. We're gonna like about 5 minutes left.
I need a burger, like a double burger, no pork. Tomato sauce with gherkins. Which one do you recommend?
Oh,
Royale.
oh, sorry. Okay. Sorry about that, guys. Okay, Luel says, when you show the demo of the dataset, is the UI updating manually, or do you have an API that gets this data dynamically? I think is asking basically on what's going on in the background there. Is it more that you prepare your data sets and you put them in a specific way and then people can make choices? And then another question from Gabriela, who unfortunately had to jump out. Can you address that issue with the gender reassignment? How can one fix that problem, given that, in thinking about the little boy? And then I think the question that I started with is that, yes, is this suite going to be available publicly, or yeah? Okay, go ahead.
Okay, thank you, Prof. So let me address Gabriela's question very quickly. So what happens is that then what will come through would be another model that basically is trained on identification of, it's just that we didn't have time. I didn't get to also present and we use this on a synthetic voice detector suite, which is loaded with a model that is able to identify all the that is trained on a data set of from child voices to young adults, teens, and also going into young males and young females on their late 20s, now going into older males and so forth. So had I loaded that model into the ASR suite, it was gonna come through before the diarization happens. It was gonna come through and basically perform detection and identify that this is basically a young baby, a young daughter, or a young female baby, and then the other is a female, an adult female, and then now diarization boxes would have been corrected with that. It's just that I did not have that implemented, but we do have it implemented on the synthetic voice detector, because it needs that. The core of it being able to detect the different kinds of voices and identify these cloned voices. As I said, uh, we will make provision that the ASL suite becomes available for researchers to basically work and playing with it, and also because that is gonna give a different fee. It's also gonna give a different feedback from the community, and they can suggest different features that will go through the next version that will be iterating and moving forward. I don't know if there is another question, Bob.
Okay, that's fine. Quick one. There was just some questions on the training. I know you didn't get an opportunity to really go through what the training would look like. Is it just fine tuning on pre-trained models, or can you train from scratch? Can you talk about that? And then number two, how does the research on your work might address lexical ambiguities?
Lexical ambiguities, that is sort of like a complex one that still needs a lot of research that is going on. But basically, yeah, I think I remember the other question was, is it so it was about the data sets and how they are being processed as well. So the data sets on the back end of the fine tuner suite is that we have studied each and every single one of the suites, of the data sets, NCHLT, and we went through each and every different available corpus that is there, and we saw that they all follow a structured approach whereby they all have standardized it. So then we defined that, okay, this is the NCHLT standard. Went through all different Lwazi data sets for different languages, found that everything is still standard, and then we said this is the Lwazi standard. Went through all different samples of common voice and discovered that common voice still also requires that each and every one of them have the same standard files, same transcription files, and same speech files and all that. And then we define that as the standard file. So basically what Python does is then it goes into the folder and starts to search all these files. And if it detects these number of files and recognizes them, that, okay, they are valid, they're having speech data and they're having transcriptions and they are in this particular format, then it identifies it as Lwazi. And it knows how to basically tokenize Lwazi. It tokenizes Lwazi differently from how it tokenizes Common Voice or basically NCHLT. But the key point when everything else is tokenized is that now when we feed the tensors and we start to perform training and fine tuning, then as I said, those NumPy arrays now take these vectors and start to work on training and improving and fine tuning the Whisper model, which is at the core of the system. So basically, that ends up making it standardized, and that regardless of the data set that you use, the same results are being achieved. So if you are to take Afrikaans Common Voice and Afrikaans Lwazi and you train with them, you are basically, the variability will be on what error rates because of the quality of the data set, but the output is going to basically just pretty much be not that, far from each other and so forth, unless you have altered the parameters when you were choosing your things like learning rate and things like gradient accumulation and so forth that you've set differently from each training set. But if you just made the same parameters, and then there shouldn't be too much of difference in terms of output that you will get or that you will achieve. The model should be fine-tuned and be able to perform well on low resource language.
Okay, I think that will pretty much be it. Thanks. In this case, we just want to make sure we are within the time, but thanks everybody who's was able to come to these sessions. I think it's been very useful for many people. We will. I think there was a question about recordings. Recordings will be available probably in a couple of hours for everybody. There are links in also to just follow different spaces where you can find us. And I will also put a link in a second to follow Dr. Hope Mogale's work. He is available on LinkedIn, and there are other ways to just get in touch with in touch with him and in different ways. So we're really looking forward to people figuring out how to how can we expand some of this work, and then also find ways to collaborate. We're always looking to do these types of things. So thank you everybody for coming in today, and then we will let you know when our next seminar series starts is just that from now on in March we will have a postdoc series, and then likely the next one will be in May, also connected to a lot of Africa Week events here at the University of Pretoria. So thank you, and yeah, see you next time. Thank you, Hope.
Thank you, Prof.